Dear students, in the previous class we have studied about the different types of conductors, that is the metallic conductor, also known as the electronic conductor and electrolytic conductor. We also studied about the resistance which is offered by the conductor to the flow of the current. The reciprocal of resistance is conductance, and then we studied about resistivity and conductivity. Now, the next topic of this unit is molar conductance. If we take 1 mole of the electrolyte, then the ions produced by this 1 mole of electrolyte offers conductance. This conductance is molar conductance. Let me define it. It is defined as the conductance of the volume V of the solution containing 1 mole of the electrolyte kept between 2 electrodes with area of cross section A and distance of unit length L. The symbol for the molar conductivity is lambda with subscript small m. Mathematically, lambda m or the molar conductance is related to kappa, that is conductivity, by as per equation 1. Lambda m is equals to kappa upon C, where C is the concentration, which is expressed in moles per liter. Lambda m is also equals to the product of conductivity and volume. K kappa is conductivity and capital V is volume. The unit of the molar conductance. By substituting the units of the kappa and volume or concentration, we get the unit of the lambda m as Siemens meter square per mole. Variation of conductivity and molar conductivity with concentration. Let me again revise you what is conductivity. We have already studied in the previous class. Conductivity or specific conductance is the conductance of 1 centimeter cube of the solution. It depends upon the ions which are present in 1 centimeter cube of the solution. And the molar conductivity is the conductance of the ions produced by 1 mole of the electrolyte. So, there is a difference between conductivity and molar conductivity. Let us study how the concentration or dilution affects both of them, kappa and lambda m. First of all, effect of concentration on conductivity. As we know that it depends upon the number of ions in 1 centimeter cube of the solution. So, when the solution is concentrated, the number of ions is more. But as soon as we dilute the solution by adding some more solvent, the number of ions in 1 centimeter cube of the solution decreases, and since the number of ions decreases, the conductivity also decreases. The behavior is same for strong and weak electrolytes both. Effect of concentration on molar conductivity. In this case, the behavior will be different for the strong and the weak electrolyte. I have explained you. Strong electrolyte is the electrolyte which dissociates almost completely, and the weak electrolytes never dissociate completely. So, the behavior is different for strong and weak electrolyte with dilution, or you can say concentration. We will discuss it one by one. We know that just now I have told you lambda m is equals to kappa into volume, that is conductivity into volume. Now, we are diluting the solution, that means we are increasing the volume. When the volume increases, lambda m increases. Now, for the strong electrolyte, let me explain you what happens exactly. In the strong electrolyte, we know that it is dissociated completely. So, on dilution, there is not much appreciable increase in the number of ions, but the mobility of ions increases when we dilute the solution. And when the mobility of the ions increases, the lambda m automatically increases. With the help of the graph, you will be able to understand the behavior of a strong and the weak electrolyte. In the case of the strong electrolyte, also what happens is, when the solution is concentrated, there is strong interionic attractions because ions, they don't have volume to move, they don't have space to move, and since they are oppositely charged, they attract each other and their mobility decreases. As soon as we increase the volume, the interationic forces decreases and they are now free to move and they contribute to the molar conductance. In the case of the weak electrolytes, as I have told you, they are not completely dissociated. On dilution, the dissociation increases. Dissociation increases, that means the number of the ions also increases. When the number of ions increases, they will automatically contribute towards the molar conductance and hence the molar conductance increases. Now, let me explain you the Debye-Huckel-Onsager equation. The Debye-Huckel-Onsager equation correlates molar conductance at any concentration with the molar conductance at infinite dilution. Let me tell you what is molar conductance at infinite dilution, which is also known as limiting molar conductivity. What happens in the case of the strong electrolyte? When we dilute the solution, there is a slow increase in the molar conductance and soon it approaches the maximum limiting value of the molar conductance. And after some dilution, it approaches the limiting value, and after which on further dilution, there is no further increase in the molar conductance. This is lambda m naught. Lambda m and lambda m naught are related by Debye-Huckel-Onsager equation. Lambda m is equals to lambda m naught minus a root c, a constant. From this relation, you can very well see that as the concentration approaches 0, that is infinite dilution, lambda m becomes equals to lambda m naught. Let me explain you the molar conductance for strong and weak electrolyte with dilution. In the graph, you can see that there is a blue line for strong electrolyte, and you can see that as we are decreasing the concentration and increasing the dilution, the blue line soon approaches and touches the y-axis and we get limiting value of molar conductivity. This is the behavior for strong electrolyte. The examples of the strong electrolytes are like potassium chloride, sodium chloride, hydrogen chloride, etc. For the weak electrolyte, there is a red line or a red curve you can see. For the weak electrolyte, there is a slow but continuous increase in the value of the molar conductance when the concentration approaches 0. But from the graph, you can very well see that the red line becomes parallel to y-axis and it is never touching it. That is, even by the extrapolation of the curve, that is the red curve, we will not get limiting value of the molar conductance for weak electrolyte, because the weak electrolytes are never completely dissociated. So, I can say that the lambda m value for the weak electrolytes can never be calculated experimentally. Then what is the method by which we can calculate, we can find out the lambda m value for the weak electrolytes? That is the Kohlrach's law. Let me explain you what is Kohlrach's law. Kohlrach's law of independent migration of ions. The scientist Kohlrach, he observed that the ions, they have a definite and independent contribution towards molar conductance. He observed the dissociation and contribution of different ions in different electrolytes, taking strong and weak electrolytes. And then he gave his law, that is Kulrash's law of independent migration of ions. The law states that limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. For example, lambda m infinity for sodium chloride can be calculated by simply adding the contribution of the sodium ions and the chloride ions. Kulrash's law is very useful in calculating the theoretical lambda m value for the weak electrolytes, which otherwise cannot be found out experimentally. We can just take the values of the contribution of the different ions by taking them from the suitable strong electrolytes, and simply by adding those values we can find out lambda m value for the weak electrolytes. Using Kulrash's law, we can also find out the degree of dissociation, that is alpha, is mathematically equals to lambda m upon lambda m infinity. We can also find out the dissociation constant, that is K. K is equals to C alpha square upon 1 minus alpha, whereas alpha is the degree of dissociation. Let me take a suitable example of a weak electrolyte. Acetic acid is a weak electrolyte. It will not dissociate completely. So, to calculate its molar conductance experimentally is impossible. But by using the Kulrash's law, I can find out its limiting molar conductance by just simply adding the contribution of the acetate ions and the hydrogen ion. But these values are taken from a strong electrolyte. Let's take an example. To find out the lambda m infinity or the limiting molar conductivity of acetic acid, I have to take the values from 3 strong electrolytes. These are sodium acetate, which has the contribution of acetate and sodium ions, hydrogen chloride, which is the contribution of the hydrogen and the chloride ions, and lambda m infinity for NaCl, which is the contribution of sodium ions and chloride ions. Simply by adding and subtracting the suitable values, we can find out theoretical value of lambda m infinity of acetic acid. So dear students, just now I have explained you the effect of dilution or concentration on conductivity and molar conductance, and I have also explained you the Kulrash's law and its application. I am sure all these concepts are clear to you.